So base peak, this thing should be the, what, largest peak? Okay, or largest peak. Molecular ion, what does that tell you? Molar mass. How about this right here? What about the difference between chlorine and bromine in the mass spec? Cl is going to be what? Going to be 3 to 1 for the ratio of the peaks. And what about Br? That's 1 to 1, right? IR versus NMR. What are some of the things? Let's start with IR. What are some of the things that we want to pull out of IR? What kind of information do we want to get out of the IR? Functional group. So let's say you were looking at 3200 to 3600. What am I looking at? OH or NH, right? Both those things would be there, right? But what's the difference between the two? OH is broad. So if you think you have an alcohol or carboxylic acid, then that peak has to be very broad, right? But if I'm looking at NH, so OH, broad, NH, sharp, right? Primary amine is what? How many peaks? 2 peaks. Secondary amine, 1 peak. And that's a good kind of differentiation between the amines and the alcohols. Now, if you have a carboxylic acid, right, then that whole region gets wiped out because of all the hydrogen bonding. And if you're trying to differentiate between an amine and an amide, what do you have to look for? The difference between an amine and an amide is going to be a C double bond O. The next place you're kind of like focusing in on is around 3000. Above, that's going to be what? CH unsaturated. Below, that's going to be CH what? Saturated. Now, there's an area around 3000 that we use as kind of like a secondary kind of clue to another functional group. And that is right around 2800. You should actually see what? 2 peaks for aldehyde. Okay? But again, and I'm saying this, the IR may not be the best place to look at what? Aldehyde. So maybe we can look at a couple of these as we're talking, and we can see what we're talking about. So here's an aldehyde one, and sure enough, the peak's what? Right here. Or what are we talking about? About what? 2800, right? Now, what's this peak right here, though? This is the C double bond O, right? For that aldehyde. Now remember that aldehydes are what? Okay, so it's this H that we're kind of talking about here. Is the IR the best place to differentiate that you've got an aldehyde? No, let's it's actually in here, isn't it? So if we have an aldehyde, right, what should we see? We should see a peak between where? 9 and 10. And again, that peak there. Alright, so what we got is right here, right? That's that CH, but really it's the H, right? Of the aldehyde again. So we're looking at aldehyde. The other thing I want to point out is like right down here, this is the C double bond O, right? So how do we differentiate between an aldehyde and a ketone? The aldehyde will have this single peak between 9 and 10. The ketone will not. But each has their C double bond O between 190 and 220. So we kind of differentiate the aldehyde and the ketone away from the acid and the ester, because the acid and the ester would have their peak for the C double bond O down in this region. Okay, so this one here was actually turned out to be a ketone, right? So this one turned out to be a ketone. Why? How can I tell that this is a ketone? I still have what? C double bond O here, but up here I have what? No peak, right? 9 to 10, which says what? No aldehyde. So there we have a good differentiation between the two groups. Let's go down and take a look at the acid now. Okay, here was an acid. What do we notice about this one? If we look over here, we notice that the whole region up around 3000 is completely wiped out. And what's causing that? The hydrogen bonding going on with this acid. But the big thing on this one is what? The big thing is this right here. This is the what? And I'll underline what it really is, right? This is the acid proton. This is the acid proton because it's now between what? 10 and 12. And that's how you know we're looking at an acid. Now if that isn't good enough, then you could also look at the fact that, notice this is much lower than 190 now, and this is now the C double bond O. Now, how do I differentiate between an acid and an ester? The ester is not going to have a peak between 10 and 12, will it? The range usually is 10 to 12, but this must be really what? De-shielded. So even though this one goes past 12, it's still the proton of that acid, because acids are going to be the only things you're going to see that far down on a test. You'll either have to draw the structure and or you might have to explain why you feel that this isn't. I might sit there and say, write a brief description of why you feel the compound is this functional group versus another functional group. Yes, you'll actually get the 3 sheets. You'll get the IR flow chart and you'll get the sheets that are in the back of your lab notebook as well. Well, it couldn't be an ester because we have a peak way down here. So we see this peak down here between, we're way even past 12, like Felicia said, but this is definitely, we're looking like we have an acid. The other thing that kind of is indicative is this whole region is all wiped out from the hydrogen bonding of the OH of the acid. So we did what? Acid and ester, we did aldehyde and ketone, alcohol and amine. How are we going to tell how the benzene ring is actually substituted? First thing, mono versus di. You got to look at the integration, right? If it integrates to 5, it's mono. If it integrates to 4, then we're looking at di-substituted, right? Now, how many di-substituted cases can you have? 3, right? Ortho, meta, and para. Para, the way we can tell if something is para-substituted is we're looking for what? We're looking for a doublet of doublets. 2 and 2. What about meta? If you looked at the spectra from your M-nitromethylbenzoate lab, large singlet, right? And odds are, because they're so ugly, I probably wouldn't give you an ortho-substituted compound. So it's either going to be mono, para, or meta. Okay? If it is a benzene ring. And I say if it is a benzene ring. It doesn't have to be a benzene ring. You know, we did do some spectra where it wasn't a benzene ring, all right? How about bending and stretching? How many stretching vibrations are there? 2. You can either have what? Symmetric or asymmetric, right? But it's the bending vibrations that are kind of weird, right? They come into 2 groups. Those 2 groups are either going to be what? In plane or out of plane. So think of your motions when you're in the plane. You're either bringing what? Your arms together, which looks like you're doing some type of scissoring move. So that's scissoring, right? Or what? Rocking, right? Because you're rocking back and forth. But if you break the plane, then you're either what? Wagging or twisting, right? Wagging is if you look like you're what? Probably worshiping somebody. But the twisting looks like, again, you're going back to those aerobic things. How about the hybridization of carbon and benzene? Yeah, it's sp2. Explain why benzene is stable using an energy diagram. For benzene, this distance right here, what is this from? It's resonance stabilized. For benzene, you can draw what? 2 different resonance structures for benzene. So you don't have to reproduce the exact numbers in this chart. You need to know the logistics that the height for cyclohexene and the height for, let's say, benzene would probably be what? 3 times it if it was cyclohexatriene, which is hypothetical. But because of the resonance stabilization, this thing is much lower than expected. So it's not that, again, you have to memorize these numbers, but you do have to explain. I mean, you can put 1 line and then kind of guess 3 times that height for cyclohexatriene, and put benzene somewhere in between. And there's your 2 resonance structures. One has the vertical double bond here, the other one has the vertical double bond on the other side. So because of these 2 resonance structures, remember we can kind of say they're resonance structures.